Hello, in this video we're going to be looking at two topics, two special applications as kind of a segue into a much broader branch of mathematics. We're looking at areas and distances, and what we're getting into is an area of math, an area of calculus called the integral calculus, which is the second, kind of the other main branch of calculus after differential calculus. Having said all that, now we read it on the slide, of course. So I'm going to explore second major branch of calculus, integral calculus, or kind of studying the main process that's going on there, which is integration. As with our introduction to differentiation, we're going to consider two problems, and these are going to kind of motivate and introduce the topic, as we say here. So the first is the area problem, which we want to describe the area between the graph of a function and the horizontal axis. So this one may be a little bit more theoretical, if I could spell theoretical. Let me just not spell anything. But it would be comparable to the tangent problem, where you're trying to find the tangent line to a curve. And you might just, think in the real world, kind of graph some function, find the area under it. It might be a fun kind of way to spend some time, but not a super useful thing, just more of a interesting thing. The second problem is called the distance problem. So just at face value, this would be one that we would say is more tangible, more hands-on, more real world. So in this problem, we want to find the distance that an object has traveled, knowing its velocity over a period of time. Now, by knowing its velocity, we mean that we have a description, something like a function that describes the velocity at any period in that interval of time. We are going to see, just spoiler alert, just like with the introduction to differentiation, the two problems that we looked at, the more theoretical-ish one and the more applied one, that they're actually the same problem, mathematically speaking. So for the area problem, getting started, suppose we have a function f with f of x being non-negative for all x in the closed interval a to b. So what we want to do is find the area of the region bounded above by y equals f of x and below by the x-axis between a and b. So kind of the picture of what's going on, kind of imagine something like this. And let's suppose I've got some function like this, and we'll say from a to b. So what we're trying to find then is this area here. So that's the area problem. Trying to find that area under a curve for a function that is at least not negative. So that means it's on, or maybe it touches the axis a couple spots, but it's above the, it's not below the axis. Let me jump back here real quick. Save follow-up. Use a little bit thicker marker here. If f is constant or linear, terrible thing to say, but let me say this is easy. And what I mean is, even if it's a linear like this, so not a constant function, but a linear one, when you're talking about the area under the curve, you got a trapezoidal region there, so that's something that you can figure out without calculus. Something like this is going to be a little bit trickier and more interesting, and that's the sort of thing that we're looking at. I'm going to jump back to my other pen width. Okay, so to find the area in the general case, again, the general case would be something where we've got a curve, not a linear function. We're going to start by approximating with the region that we do understand, the rectangle. So again, picture kind of what's going on here. You've got your function there, you're going from A to B, and we're going to try to estimate that region, which we said we're trying to find in red here. We're going to try to estimate that. What should I pick here? How about purple? Yeah. So we're going to try to estimate it with rectangles. Like this. Not showing up real well with the technology, I know, but we're going to use some rectangles under the curve to try to estimate that area. Maybe if I draw this again, you can get a clearer picture. What I mean is, maybe something like that. 3 rectangles in this sketch. But we're trying to estimate the area under the curve. The reason why we use rectangles is because we know a function, or we know a description, we know a formula for finding the area of a rectangle, just the base times the height. So we use something we know. Now we could use all sorts of shapes that we know, but the nice thing about rectangles is it kind of allows us to give a nice general description very concisely and quickly. So first thing we're going to do for this type of problem is we're going to figure out how many rectangles we want to use. Say we use n. So we're going to break up our interval. Remember, our interval is going from A to B into n equal length subintervals. However many that would be, n total. And each one is going to have width b minus a, which is that total interval length over n, this number of subintervals. They don't have to all be the same length, but it's easier just in the setup to do it that way. So that's what we're going to do. Now, having done that, that's going to be the base of each rectangle. The height, well, it's going to depend on points that we choose within the subinterval. So maybe something like this subinterval here, maybe I choose the point there. Whatever f of x is, that's going to give me my height. So I choose some point in the subinterval. The function value gives you the height. So that's what's called a sample point. So we got common options for sample points. If we're looking at our subinterval, we could do left endpoint. We could do the right endpoint. We could do the midpoint, right in the middle. And these first 3, they don't depend on the function at all. It's just the left endpoint of the interval, subinterval, right endpoint, or the midpoint. Now these 2, the last 2, there's some value in here that's where f is going to be maximized, or some value in here where f is minimized. If we have a continuous function on a closed interval, we know for sure that such a point is going to exist by extreme value theorem. But we don't know where it is unless we know something about the function. So maybe it's over here, maybe it's over there for a maximum or a minimum. We don't know yet. So these 2 options are much trickier. It's much more formulaic and quicker to compute for the first 3, left, right, or midpoint. So again, the area that we're trying to find is approximated by the sum of the areas of these rectangles. Each rectangle has area f of xi star times delta x. This f of xi star is the height, delta x is the width. And so in general, we should expect that as we increase the number of rectangles, we should get a better and better approximation, something that's closer and closer to the actual area. In fact, that's what happens. So for a continuous function on the closed interval AB, the area is the limit as n goes to infinity. So as we increase the number of rectangles, n was the number of rectangles, as that goes to infinity, this better and better fills in that space. Again, if you think of the picture, if I had 2 rectangles, maybe that fills it in okay, good enough for me, might be happy enough with that. But maybe if I do a bunch more, you see that it fills it in better and better. There might be little wobbles along the way. We could come up with exotic examples perhaps, but generally that the trend is as n gets bigger and bigger and bigger, this does fill in the space better and better and better, which kind of makes sense if you don't you don't have to be too rigorous with it. And in fact, like I said, if f is continuous, that limit exists, and that is the actual area. All right, so that was the area problem. We gave a way of trying to tackle that by an approximation. And for a function that's nice, namely just has to be continuous, we can find the exact value if we can compute that limit. Now the distance problem is a different problem. Now we're trying to find the distance an object travels over a period of time if we only know its velocity. So for example, suppose an object, a car, whatever you like, is moving at a constant rate of 50 miles an hour, straight direction, let's say, for 3 hours. If it's on cruise control, nothing's changed, 50 miles an hour for 3 hours, the distance traveled is 150 miles. Don't need any calculus to figure that out. But if the velocity is not constant, speed up, slow down, no one's around, you go a little faster, think you see a policeman behind a bush or something, you slow down a little bit quickly, whatever. You can imagine the scenarios. The point is that your velocity is not constant there. And we still want to answer this question, how far did we go? So it gets more difficult. This is analogous to the area problems for non-linear functions. So in the nice case, the early case, a linear function, we don't need calculus. We're just looking at either the area of a rectangle or the area of a trapezoid. The nice early case here, if you got a constant rate of change, nothing crazy. You know what it's going to be. But when it's varying, that's when it's getting more interesting. Just like with the area of the curve, when the function is varying, it's getting more interesting. So suppose we know the velocity function of an object over a given period of time. If it's positive, then the area bounded by this curve and the horizontal axis is exactly the travel distance that we want to find. So you can kind of think about it like this. If I've got a velocity function so it's positive from time period 0 to time period 1, whatever it might be, it turns out that this is the area that we want to find. You can think about that, kind of make sense of it. If you've got time on the horizontal and velocity, which is distance per time on the vertical, when you multiply those together, you're going to get your area, and it's going to be just in distance. Distance per time times time gives you distance. And that's the this makes sense part comment that I have here. So it turns out that just as we had with our introduction to differentiation, or a more real-world problem ends up being the same as a more abstract problem, mathematically speaking. In both situations, for the new case, both situations in the new setting, not the old stuff, but the area and distance problems, we're trying to find the area of a particular region. For now, we're going to focus on estimating areas, but we're soon going to see how to effectively evaluate this limit on a previous slide that gives us the exact area and see what this means in more general.